Welcome to Algebra 2. Today we're going to be doing still on Unit 1. We're going to be using Lesson 12 of Unit 1, and we're going to talk about inverse functions that undo another function. So we're going to be looking at composing functions and seeing which functions are commutative, which functions undo another function. So that's what we're doing. Your learning target today, you should be able to say, I can compose functions together and test for commutative functions. I'm going to show you how to compose functions together. We did that last lesson too. We're going to do some more composing of functions, but now we're going to add one more wrinkle into it. We're going to look at functions that undo each other, functions that are commutative, functions where I can reverse the order and I get the same result. So last time we had Frank's Fun Factory. Frank's Fun Factory took apples into machine 1, turned them into lemons, and then when the lemons went into machine 2, they came out as oranges. But Fatma's Fun Factory is a little different. Apples go in to machine 1. And then again, the machines here are analogies or symbols for a function. A function is a mathematical input-output machine. You stick x in, you get f of x out. You stick x in, you get y out. Right? There's one unique y value for each x value. So here we go. Machine 1 is our function 1. I stick my x's in. My x's are apples. I stick x's into machine 1, function 1, and it spits out lemons. I then compose the function, sticking the lemons back into my next function. In my next function, if I stick the lemons back into my next function, this time, instead of coming out oranges, my function spits out apples again. So this is a unique kind of situation. Please describe to me what happens in Fatman's Fun Factory here in the warm-up. Describe what we just discussed. And then number 2, I'm going to leave you to answer this for yourself. If Fatima's Fun Factory is being sold on TV, would you want to buy it? Explain why or why not. Again, I want to activate those upper reasoning skills where you're explaining why or why not. That's the more important part. Whether you say yes or no, that's necessary, but then explaining why or why not is the really important part to that question. I'll leave you to it. You can pause the video here if you need more time to write. Of course, you probably do, but I'm going to get right into it. All right. So here's what we're going to be doing. Today we're going to be composing lots and lots of functions. This is a skill we need to be able to get good at. And you get good at skills by practicing them. So we're going to practice them. All right. So I'm giving you an example over here. And I'll explain this example in a minute. But I want to show you how I've set up this packet here. The functions you'll be composing are after the next 2 pages. So here's this page. We're going to do 4 of these together. We're going to do these 4 together. I'm going to show you how to do them. I want to see if you can do at least 2 here. Compose at least 2 functions here. If you do 4, that's great. I want to see you do at least 2. And then here are our functions. Now I wish, when I look at how this printed out, I kind of wish this had printed out into where I had set A, B, C, and D all together. That would have been ideal. I should have formatted this a little nicer. I'll keep working on trying to format this a little nicer and squeezing these things together. Docs and Word are weird about sizing, and once things get too big, it spits something out somewhere else. And so I think what I decided was I was going to put set A and B together, and then C and D over here. I know that's not ideal, but that's how I could set it up at the time. So we're going to be composing functions. Let's talk about this example here. We read this as the h of a of 5. Function h of a of 5. The function h composed into a where the a of the function a is 5. All right? Here's how we do that. We first need to know what function a is. And again, we have to go over here to set a to find function a. Function a is 3x minus 4. Do you see that? On set a functions, the a of x is 3x minus 4. So here's the example. 3x minus 4, what is my a of 5? My a of 5, plug 5 in for my a of x. The function a is 3x minus 4. What I plugged in was I plugged 5 in for x here. I plugged 5 in for x. That's the a of 5. Plug 5 in for x, I get 3 times 5 minus 4. Well, 3 times 5 is 15. 15 minus 4 is 11. So we have 11 out here. Then what we got to do is we got to take this 11, we got to plug it back into the next function. That's the composition part. Now we got to plug 11 into the function of h, lowercase h. So now I have to go back and find where is my lowercase h function. My lowercase h function is right here, 3x plus 12. 3x plus 12. So I am going to take 3x plus 12, 3x plus 12, and I plug 11 in there. I plug 11 into my 3x plus 12. So now I have 3 times 11 plus 12. All right, well, 3 times 11, use your calculator, that's 33. 33 plus 12. That's going to be 45, right? 45. Use your calculator. If that doesn't come to you, we're going to practicing this as skills. As you start practicing a skill, eventually it starts to become almost automatic, right? You start learning how to play an instrument, and eventually it's almost like you're not even thinking of it. If you're learning piano, you get to a point where at first every keystroke you have to think about, da 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 da, and then eventually your fingers are just moving. It's muscle memory. It's that memory that comes from habit. It's stored. Habit and skills like this are stored in a different part of our brain from our thinking memory, but we need to do lots and lots of repetitions in order to develop that habit memory. All right, and math is very much the same. We're going to do things lots and lots of times. I know that's tough. I know, it's difficult to practice. Practicing is hard, and sometimes it even feels boring because you are being repetitive. But that's what's required to really get this stuff to be automatic. So it's easy. I want to get it so it's easy for you. And to make it easy, we've got to do something that might be a little difficult, a little hard, okay? It's just skills. It's just life. Well, we can do it. You can do it. All right? The summary of the h of a of 5 is 45. We're going to continue doing that. Okay. Now we're going to do one on our own, all right? I'm going to show you 4 of these, and then I want you to do at least 2 on the next page to get at least that minimal. And give me 3 for that 80, and give me 4 for 100 on this page. But 2 is good enough. 2 is fine. Let me compose these. Let me go over here. I can choose any of these any way I want. I'm going to compose one set at a time. So let me compose 2 from set A, 2 from set B, 2 from C, and 2 from D, all right? What am I going to compose? I want to compose, how about I just compose these 2? I already composed the G and A. Oh, I did A and H. I did A and H just now. Let me compose these 2. The B of X and the H of X, all right? I'm going to compose this as the B of H of, what could it be? I'm trying to think of a good number, of 4. Okay? The B of H of 4. All right, did you see that on your screen? What I wrote right there, the B of H of 4. All right, so now how am I going to do this? I need to go and write about what the B of what each function is. This says the B of H of 4. So the first thing I need is the H of 4. H of X is 3x plus 12. All right, so to do the H of 4, I'll need to put 4 in for x here. So 3 times 4 plus 12. All right, you with me so far? The B of H of 4, I plug 4 into my H of X. I got that on my next page. The H of X is 3x plus 12. Plug in 4 for x. 3 times 4 is 12. 12 plus 12 is 24. Now I have to plug 24 into my B of x. My B of x is 3x minus 12. My bx is 3x minus 12. I'm writing that down to remind myself what it is. Now I got to plug 24 in for this. 3 times 24 minus 12. All right, I might go to my calculator for this. I'm thinking that's going to be 72. Use my tool to make sure I'm right. 3 times 24 is 72 minus 12. 60 equals 60. So I can rewrite this. The b of h of 4 equals 60. All right. I can also reverse these. I could actually do set A. I could reverse these and say, what about the h of b of 4? The h of b of 4. All right. So I'm going to be composing b into h and 4 into b. So what is the b of x? The b of x is this 3x minus 12. 3x minus 12. So I'm going to plug in 4 for my b of x. 3 times 4 minus 12. 3 times 4 is 12. 12 minus 12 is 0. So I get an output of 0 where the b of x, where x is 4. Now then I need to plug 0 into my h of x. What's my h of x? Well, it's the thing I did the first time. The first function I did over here. Remember? That's my h of x. And I can get that from my next page over here. I want to confirm my h of x. My h of x is right here. Oh, nope, that's set C. H of x is 3x plus 12. And back to my page. 3x plus 12. I need to plug 0 in for x this time. So 3 times 0 plus 12. What's that equal? 3 times 0 is 0. 0 plus 12 is 12. I get 12. So the h of b of 4 is equal to 12. Notice that pattern that just happened here. The b of h of 4 is 60. The h of b of 4 is 12. And that's what usually happens. What usually happens is that when you compose functions, if you switch them around, you're going to get different numbers depending on what happens. Usually that's what happens. But sometimes there are functions which are the inverse of each other. And when you find functions that are the inverse of each other, if you stick a number in one function and put that output into the next function, you'll get the same number as if you had reversed the order of composition. If you had done, when I do b and h are obviously not commutative. B of h are definitely not inverses of each other. 3x minus 12 is not the inverse of 3x plus 12. So this didn't come out the same, but it can. And the next example I'm going to choose are going to be two functions that are going to be inverse of each other. And we're going to watch how that folds out. So this time, looking at these two, and I think these two, g of x and a of x, I think those are the inverse of each other. So I'm going to use these for my next function. I'm going to talk about the g of a of, what number should I use? I'm going to use 3. I'm going to use 3. So the g of a of 3 and the a of g of 3. So I'm going to write that over here. The g of a of 3 and the a of g of 3. And I'm going to write down my functions just so I remind myself so I don't have to keep flipping. The g of x is 1/3 times x plus 4. 1/3 times x plus 4. A of x is 3 times x minus 4. 3 times x minus 4. And then when I reverse it, I'm going to do the a first. So I'm going to put 3x minus 4 over here. That's my a of x. And my g of x is going to go over here. It's at 1/3 x plus 4. All right. Good so far. So just taking the equations from my other page over here, my g of x and a of x, and I'm writing them down. Keep everything straight, keep everything transparent and legible. Okay, so now I can do this. The g of a of 3. Well, the a of x is 1/3 x plus 4. So I got to plug 3 into the a of x. So 1/3 times 3 plus 4. What does that equal? Well, use your calculator. It's going to be 1, but let me show you how to use your calculator. I'm going to use my parentheses. 1 divided by 3 times 3. 1. If you think about this, 1 over 3 is a fraction, but 3 is also a fraction. It's 3 over 1. These ones cancel each other. These 3's cancel each other. I get 1. So 1 plus 4 equals 5. Now I have to put 5 into my g of x. My g of x is 3x minus 4. Right, I want to make sure I got that right. I wrote down my g of x is 1/3. Oh my gosh, what did I do? Did I goof this up? Okay. So this is a word of warning. When you do this, you got to make sure you keep everything straight. So let me see what I did here. I put 1/3 plus 4, and I thought that was my a of x. I should have written that down, but this was actually my g of x, and this is my a of x. A of x, if you look on the next page, again, I wrote things down so I wouldn't forget, and yet I still made an error. And it's one of those things you just got to attend to precision. Be careful. So let me show you again. Well, here's my error for all to see. The g of x is 1/3 x plus 4. Maybe some of you, while I was writing this down, were screaming at me, yelling at me, saying, "Oh, Mr. Stoll, you're doing it wrong." The g of x is 1/3 x plus 4. This is the a of x. All right. So what did I really do just now? I first did the g of x. So I need to change this. I need to change the order of my symbols here because I got this reversed. What I did first was I was composing 3 into the g of x. So my g has to go here, and my a has to go there. I'm sorry if I've goofed you up if you were writing that in pen. But this is where we are on track now, all right? The a of g of 3. The g of x is 1/3 plus 4. We plugged 3 in. We get 5. Now we plug 5 into our a of x. So yes, it was an error. We can totally recover from it. We just figure out what we did wrong and we fix it. Mistakes happen, and mistakes is where we learn. You can better believe I'm going to be more careful the next time I write a composition of functions based on an embarrassing mistake like that. All right? I plugged 5 into my a of x. 5 times 3 is 15. 15 minus 4 is 11. Use your tools if you don't know. If you don't want to do that math in your head, I fully support using your tools. Use that calculator. That calculator is your friend. So the a of g of 3, that's 11. We composed this function. All right? Let's compose it the other way, the g of a of 3. This time we're going to do the g of a of 3. All right? Well, the a of 3, let me plug 3 into a. A is 3x minus 4. Well, I got to plug 3 in for x, so it's 3 times 3 minus 4. 3 times 3 minus 4. 3 times 3 is 9. 9 minus 4 is 5. Well, look at that. We got the same answer when we plugged the same number in for the different functions. Let's see what happens next. Plug 5 into the g of x. The g of x is 1/3 times x plus 4. We're going to plug 5 in, so 1/3 times 5 plus 4. 1/3 times 5 plus 4. All right, well, what we're going to get is we're going to get a fraction there. So when I plugged in 1/3 times 5 plus 4, I got 5.666. Now, you can't really see what I'm doing there, can you? When I had 1/3, 1 divided by 3, times 5 plus 4, I get this 5.66666. That I don't like this long number. This is what it's telling me, that this is an irrational decimal. That 666 continues on forever. And the calculator is just trying to help me out by rounding it at the end to give me something a little bit more precise. I'm going to cough on. All right, so I don't mathematicians like precision. We like it when things are just nice and neat and wrap up. So this might be good enough for NASA in terms of precision. It's not good for not good enough for mathematics. So we want to turn this into a fraction. And guess what? Your calculator can do that for you. Your calculator can turn this into a fraction. Press the math button. Do you see the math button right here? It's below the green alpha button. Oh, maybe I need to. Below the green alpha button, there's this button called math. You press that, and you see how that FRAC. I wish they just write this out and say fraction, but they're going to give you this word called frac. You're supposed to know that that's fraction. I press 1 for fraction, and then it's going to give me this, and I press enter. It's going to turn my decimal into a fraction. Now, fractions, even though the number decimal is irrational, the fraction is nice and neat. It's precise. So I would say that the g of a of 3 is equal to 17 over 3. 17 over 3. That's the exact number. And while I thought these two functions might be commutative, I'm going to show you some commutative ones. Apparently these two functions are not commutative. That these two functions are in fact not commutative. I reverse the order with the same number, I get different results. So we've done 4. We've done 4. We've 4 compositions of functions here. You still have set B, C, and D to work with. You can use any of those, anything you want, to compose these into each other. I would like you, this next page, here, choose some functions and compose them. Pick, 2 functions from any given set. So you could go over here and maybe you say to yourself, oh, I don't like the square root stuff. I'm going to compose the p of x and the j of x. That's fine. You can do that. You can go over here, and we're going to say, this time I'm going to be really careful with how I do this. I don't want to make that mistake again. I'm going to compose the p of j. The p of j of what's a good number we could do this with. I like 5 for this one. I think 5 of 5. You, of course, could use any number. Why did I choose 5? Let's talk about why I chose 5, because I want you to be able to pull these numbers out too. I chose 5 because I'm looking at that and I'm thinking, okay, I've got 15 here, I've got 5 here. 5 times 5 is going to be 25. So if I plug it in here, 5 times 5 is 25. 25 minus 15 gives me 10. That's a nice number. And then if I plug 5 into this one, 5 times 5 is 25. 25 times 3 is 75. 25 minus 5 is 70. I get some nice numbers. So I just picked a number that gives me nice numbers. If I chose a different number, I would get numbers that aren't as nice. It still works. I had a student a couple years back that he just like to choose easy numbers. He chose 1 as a number that works very well for a lot of these, right? 1 times 1 is 1, and then 1 minus 15 is negative 14. That works too. You could choose 1. 0 is one that really makes a lot of these really nice. 0 times 0 is 0. 0 minus 15 is negative 15. If x is 0, 0 times 0 is 0. 0 times 3 is 0. 0 minus 5 is negative 5. You choose 0 and your life is easy. Your life gets easier when composing functions. You can totally do that. I chose 5 to keep life interesting, but you don't have to. I'm trying to show you some selections and some means. 2 is a nice one. It's not as nice as 1 is 0, but still keeps things usually pretty nice. So that's what I want from you on this next page. You're going to have to pause the video here, do this, and this time I'm going to write down very carefully I'm going to do j of x first, right? So I'm going to write j of x is equal to x squared minus 15, and my p of x. my p of x, I'm writing a little bit smaller now, then is 3 times x squared minus 5. 3 times x squared minus 5. All right, if you can't write small enough to fit that in there, you can use whatever other space you want. I want you to compose two of these functions. I want you to compose these functions, just to have you do some of these independently. Pause the video here, try them on your own. I'm going to do some on this page, but pause the video. Please try to do these on your own. I'm going to try to go through the classwork completely. I'm going to leave you mostly on your own for the check for understandings, but I want you to try some of these on your own. This is the kind of I've done the I do. I've shown you how I've done it. Now let's do what we do. You try it, and we'll go over it together. All right, and then the next on the check for understanding will be a you do. You do it on your own completely. All right, pause the video here. Give me at least 2. Give me 4 for 100%. Okay, hopefully you've unpaused the video and you've worked on a few of these. I don't know which ones you picked, so I'm just going to pick the ones that make sense to me. All right, so I have here the p of j of 5. I plug 5 in for the j of x. I get 5 squared minus 15. I already talked about this. 5 times 5 is 25. 25 minus 15 is 10. I did that in my head. You might want to do it in your calculator. Use those tools. I'm now going to plug 10 into the p of x. I get 3 times 10 squared minus 5. I'm going to do the parentheses first and the exponent first. 10 times 10 is 100. 100 times 3 is 300. 300 minus 5 is 295. I did that all in my head. You might want to use your calculator. Let me show you what that would look like. 3 times 10 to the second power minus 5. Boop, 95. Wasn't that easy? Use your tools, unless you feel really confident with doing your mental math. If you do, that's great. If you can do the mental math, it's even quicker than the calculator. But if you're struggling, use the tool. It's so helpful. All right, so now we have p of j of 5 equals 295. All right, I'm gonna cough. Hold on. I hope that cough didn't come through. Sometimes it delays a second, and then I cough and it still gets on the recording. So I apologize for that. Let's do a few more to get us towards that 100%. All right, let's go to set C. What two functions do I want to try here? Well, I'm seeing these, which are cube roots. You know what? I don't want to take you on a spin of cube roots, but I don't want us to be afraid of square roots. So let's do some square roots. I'm going to take on the challenge of the f of x into the d of x. All right, so now I'm looking at this to make this nice. All right, what number makes this nice? Does 1 make this nice? 1 times 3 is 3, plus 5 is 8. That's not nice. 2 times 3 is 6. 6 plus 5 is 11. That's not nice. 3 times 3 is 9. 9 plus, no. 4, 12. 12 plus 5, no. 5, 15. Trying to find a good number here that makes this work. What if x is 25? 25 times 3 is 75. 75 plus 5 is 80. Oof. All right, so I gave this some thought. And I'm thinking I'm going to do the f of d of 5. And again, I want some nice numbers. This isn't going to come out with a nice rational number. It's not going to come up with an answer that is satisfying for you as a student who has been doing is working up to things. It will come out with a nice number that mathematicians will be happy with. All right, so actually, oh, you know what? I'm going to do 10. I'm sorry. Do the f of d of 10. All right. All right, let me show you how that works. And again, this is one of those things where you just kind of play with numbers until you get something that looks like it's going to come out f of d of 10. Any number works. Some numbers are easier to work with than others, so you have to strategize which work better. So the d of x, to help you my memory, is equal to the square root of x plus 15. And the f of x is the square root of 3x plus 5. The f of x is equal to the square root of 3x plus 5. And why did I choose 10? Why did I select 10 in this answer? Because the 10 gives me a nice answer for at least the first step, right? If I plug 10 into this, I get the square root of 10 plus 5. I'm sorry, plus 15. The square root of 10 plus 15. Well, 10 plus 15 is 25. And 25 is a nice perfect square. And we can square root 25 real easy. If you don't know what the square root of 25 is, you can use your calculator. If you don't know what numbers are perfect squares, then you need to play around with going 3 squared is 9, 4 squared is 16, 5 squared is 25. And you need to pick a number which will get you to a perfect square to make a nice round number come out of a square root function. I picked 10 because 10 plus 15 is 25. The square root of 25, as we see on our calculator, the square root of 25, on now, square root of 25 is 5. All right, so the square root of 25 is 5. That gives me a nice integer to play with on the next step. That's why I selected 10 as the number I'm going to plug into this composition of functions. Now 10, when I plug it in, the output isn't going to be quite as pretty. The f of x is the square root of 3x plus 5. So this time I'm doing the square root of 3 times 10 plus 5. I sure hope you can see that. The square root of 3 times 10 plus 5. Well, 3 times 10 is 30. 30 plus 5 is going to be 35. So our answer is going to be the square root of 35. Oh, I wrote 34. Why did I do that? I don't know. Square root of 35. Now, this is not the kind of pretty number that you are used to in mathematics. Usually, when we're teaching mathematics, we try to keep the numbers a little bit simpler than that. But you know what? Sometimes it doesn't come out even, and sometimes this is the best you can do. It's the square root of 35. Sometimes that happens, and it's good for you to see that. For you to see that sometimes it doesn't come out to be a real nice number. Now, normally I would simplify this if I could simplify it. I haven't taught you how to simplify radicals yet. We will get to that. But I'm looking, is there any numbers that are perfect squares that multiply here? Well, factors of 35 are 5 and 7. Those aren't perfect squares. Those are prime numbers. 9 doesn't fit. 16 doesn't fit. 4 doesn't fit. So I'm done. Square root of 35. That's it. I'm done. Those are two that I'm going over for at least the minimum. If you want to push for that 80, if you want to push for that 100, compose me 2 more. Remember, classwork is based on an effort-based rubric. If you give me the minimum of what I'm asking for, here is 2. 2 I've done. That gets you to that 65 that you're passing. All right, good job. Give me 3 for most of what I'm asking for. That's an 80. Give me everything I'm asking for. That's 100. Rubik's always at the bottom of every page. Give me that lower right-hand smiley face reflection to say how you feel about this so far. How you doing? You feeling like this is easy? Smiley face. You feeling like we do the sad face? Kind of feeling confused? I don't get it. Something in between. Again, that's something in between is where I want you to be. I don't expect I'm going to have a lot of smiley faces today. This is probably something where we're new at this. It's okay. When we first learn to ride a bike, we're kind of unsteady and unsure and not confident. We're going to get there. We're going to do better. All right, so we are done with these sets A, B, and C. Check for understanding. Let me show you how to use your calculator to check for compositions which are commutative. Commutative means I can change the order, I can change the community, I get the same answer. So this function into this function, give me one answer. If I flip the switch, if I flip them around and I put the same number in, I'll get the same answer out. So let me show you how to work on that. Your calculator can do a lot of this work for you, but it requires you to do a lot of fancy thinking to make this work. So what two functions did I think were inverse of each other? So I thought it was 2 times x plus 10 was the inverse of 1/2 x minus 5. So I thought these two would be commutative, and here's how I tested it. I'm actually going to delete everything I've done here on my calculator so you can see my process of testing these functions. If two functions have the commutative property, you can switch their order and they'll give you the same result. And that means your calculator can do some of this testing for you. Watch how this works. First, you have to identify two functions you think might be commutative. Then you've got to plug them in for each other. So for instance, this first function, normally I would plug in 2x plus 10. Okay? But we're composing functions here. So instead of x, I've actually got to put in the next function I think I'm going to compose the function into. I've got to put in, instead of x, I've got to put 2 times, not x, but 1/2. I've got to put the 1/2 in its own parentheses, times its x minus 5. Do you see what I'm doing there? I'm putting this whole function here into the x of that function, as if this whole function was the x plus 10. All right. Now on the next point, and the next line on y2, I got to do it the other way. I got to put this whole thing in for the x, the q of x. All right. So we're going to start with 1/2. Got to put it in its own parentheses, 1/2. Now I need another set of parentheses, open parentheses, to put this whole thing in for the x here. 2x plus 10. That's this whole function in for the x on the q of x function, minus 5. All right, now that's pretty heavy. That's confusing. That's okay. The calculator is going to make this a lot easier for us if you can do this part. If you can plug the function in for x and the other function both directions. Because I can go second, go to my table, and do you see what I've got here? Do you see what I've got here? Notice how my y1 and my y2 are always the same answer. What does that tell me? That tells me that for 12, if x is 12, and I plug 12 into this, and then plug the output this spits out into that, I'll get 12 as my answer. If I plug 12 in this one, and then compose it into this, I'll get 12 as the answer again. So these two functions are the inverse of each other. They will be commutative. Let me test another one. I need to see another one of these to see if it is commutative. So I'm looking for numbers which have the inverse of each other for both things. So there's a plus 20 and minus 27. I'm looking for a plus 27. I see a positive 9. I'm looking for a negative 9. I'm thinking that those two won't work. This is negative 2 and minus negative 2x. I don't think that's going to work. I'm looking for one that holds some promise here. All right, after giving this some thought, I had to think about it for a couple of minutes. I was thinking, okay, what about these two functions here? These two functions here, it seems promising because I have 3 divided by 4 over x, which is the inverse of 4 over 3 of x. The question is the ratio of these between the negative 9 and the positive 12 is going to lead me to a commutative function. Can I reverse order these? So I had to go through and put these in my calculator. Notice how big this is in my calculator. I'm going to zoom in a little bit by lifting my calculator up. You see that? That's what I had to put in my calculator to make this check to see if these are commutative. And again, this is only going to work for absolute values. It doesn't work for negative numbers, but it works for the positive numbers. Check this out. The first one I put in was I put the t of x inside the k of x. The k of x is 3/4, so I put 3/4 in parentheses. Put 3/4 in parentheses. And then instead of x, I put in the whole function of the t of x. That's 4 divided by 3. I had to put that in its own parentheses. I had to add 12 to that. It's 4 over 3 times x plus 12. And then I had to minus, close the parentheses out, and minus 9, because that's what the k of x requires. In the next line, I did the opposite thing. I'm now going to put the k of x inside the t of x. So the t of x is 4 divided by 3. That needed its own parentheses in the calculator. I then needed to use another set of parentheses to put in for x. I'm going to put that whole function k of x, 3/4 times x minus 9. I'm going to put that in, but 3 divided by 4 needs its own parentheses. So it gets its own parentheses. So 3 over 4 times x minus 9 goes in next. Plus 12, because that's what I need at the end of my t of x. And I go to my table, and look what I have here. I have, now again, it doesn't always work for negatives, but my y1 values and my y2 values are always the same. I can put the same number in these two functions. I can switch the two functions around, and I can get the same answer. That's how we can test whether the composition of two functions is commutative. It almost never happens. It's very rare to find two functions that when you compose them, you get this. Like that first thing I gave you, this is a commutative function. I put apples in, it spits out lemons, it spits apples out. You'd almost never want to compose a function like this, because what's the point? What's the point? I put it in, it spits out something different, but then it gives me the same thing I'm putting in. It's almost like I don't need the function. But that can happen. It can happen, and you know how to test for it. If I wanted to do this the hard way, I would then have to stick this in. Let me do this. This will be easier. 2 times 1/2 x minus 5 plus 10. I have to figure that out. I have to pick a number. I'm going to pick a number 1. 1 is easy. 1 times 1/2. Actually, let me pick 2 to make this easier on me. I'm going to pick 2. 2 times 1/2 is 1. 1 minus 5 is -4. -4 times 2 is -8. -8 plus 10 is 2. So if I use 2 as my number, I get 2 out. Let me do it the other way. I already stuck this one inside that one. Let me stick this one inside that one. Now I have 1/2 times 2x plus 10, minus 5. I'm going to stick 2 in. 2 times 2 is 4. 4 plus 10 is 14. 14 divided by 2, or times by 1/2, is 7. 7 minus 5 is 2. So as you can see, the easy example, I stick 2 in, I get 2 out. I stick 2 in, I take 2 out. These compositions are commutative. Not all these compositions are commutative, but each one of these compositions has a commutative pair. So I want you to answer these questions. What do you notice about the pairs of functions whose compositions are commutative? What do you notice? Are you seeing a pattern? Describe the elements of each function rule and how you think this relates to the special relationship. I've already talked about it and kind of intimated and suggested. I want you to use your geometry brains, write something in here, what you think, how you think you could pick out which of these are commutative and which are not. And then create two function rules whose compositions would be commutative. That's going to be a challenge for you, I think. That's going to be a frowny face. Let me think. How do we do this? Let's do 3x plus 15 and 1/3 x minus 5. Let me test if these are commutative or not. Trying to use that pattern of the coefficient has to be inverse, and these have to have the right ratio relationship. This is 3 times x plus 15, it's going to be 1/3. It's almost like I divided that whole thing by 3 and minus 1/2. All right, so 3 times x has to be this whole function. I have to put 1/3 in there times x minus 5. Oops, I goofed it. Did I goof? No, I'm good. Now I add 15. Sorry, I thought I messed up. I'm okay. I just need to remember to put that 15 at the end. I go down the next. Now I'm going to put, so I just put this function inside that function in my calculator. Now I want to do the reverse. I want to put 1/3 needs to get its own parentheses. Instead of x, I'm going to put in this function here, 3 times x plus 15 and minus 5. Is this commutative? You tell me, explain why I didn't have you make up your own in case you don't see the pattern here. That's the check for understanding. After you pause the video here, complete check for understanding. After that, give me the reflection. Tell me how things are going. All right, now we're going to do the homework. Connecting representations. Which of these representations belong together? So how am I going to do this? I need to find out which one has the coordinate point negative, where x is -2, y is 0. Where x is -2, y is 0. Nope, not there. Where x is -2, y is 0. Yep, that one fits. Let me see if this keeps fitting. Where x is 3, y is 0. Where x is 3, y is 0. That fits. And where x is 4, y is 0. Hey, that fits again. These two are going to be connected. You see how I did that? Real simple. Real simple. All right? So now I'm looking for, okay, where x is -2, y is going to be 0. Where x, that doesn't fit. Let's see. Oh, this one, oh, you know what? I'm noticing, hey, wait a minute. This one fits for all these too. This one and this one, the coordinates fit. So I'm going to need to decide, maybe I was a little hasty here. Again, making mistakes helps us learn. I need to pay more attention to these infinity signs that are going on here. This one says that as my x's go towards negative infinity, my y values are going towards positive infinity. I originally made a connection that this one all fits because I just assumed that the coordinate points fit. They must be connected. But let's look closer. As my x values go this way, towards negative infinity, this graph shows my y values are decreasing. It's not what's being represented here. Let me see if that fits over here. Where my x values are decreasing, going negative to the left, this one, the y values are going up. This does fit. These two are connected. These two are connected. Where my x values go towards positive infinity, my y values are going down. And yes, I can see that as I'm going to the right on this graph, my y values are going down. Let me pay more attention to the domain over here. As my x values go negative, my y values are going negative. Oh, that's exactly what's happening. As I'm going this way to the left, my y values are going to go down. As I approach infinity the other direction, going this way on this graph A, my y values are going up. I have a connection. So now I see, being a little bit more careful to do this. So now I have to pick out some points. All right, I'm going to say this point, and oh, I don't see another good point here, but I would really like one. But I don't see one. So let's say where x is 3, where x is 1, 2, 3. Where x is 3, y is 0. Where x is 4, y is 0. I do have those nice points. And then I'm going to give my domains and range. All right. So as x goes negative infinity, my y values are going up. My y values are going up to positive infinity. Feeling good about that? As my x values go towards positive infinity, what are my y values doing? They're going up towards positive infinity. As my x values go this way, my y values are going up. Homework's done. Give me the smiley face. How you feel about that? Have a great day.